We manipulate the doping level. So that means that if you just have a semiconducting material, as the name suggests, right, it doesn't conduct so well. To make it conduct well, you need to dope it. I'm an associate professor of physics at the University of Groningen, and I work on the physics of novel semiconductors and devices. What we try to do is, in close collaboration with chemists, is to design novel materials, organic semiconductors we call them, and we use these materials in things like light-emitting diodes, solar cells, thermoelectric applications. If you want to harvest your own body heat for a watch or some kind of sensor, maybe a glucose sensor for example, you're not going to use a steam engine. You need something way smaller, and that is something that thermoelectrics can do. And more specifically, organic thermoelectrics. For a thermoelectric device, you need current and voltage, so you need to have proper conduction of current, proper conductivity. This is a key step, that we can manipulate how many charges we have in the material. That is what we call doping. We have a slab of semiconductor, we dope it, so we add something neutral, maybe a molecule. What we want is that these dopants all give up an electron to our semiconductor, So 4 dopants also give us 4 electrons, so that means that we have 4 pluses. Because I put in something neutral, I take out something negative, that means that I will have something positive. Now there's 2 problems here. One problem is that the electron and the ionized dopant have attraction, so this electron wants to go back, and of course that limits the flow of these electrons. The other problem is that if this electron wants to move to the right, for example, it will sense the presence of all the other electrons. And there's repulsion, so that makes it more difficult for this electron to move to the right. This is one of the things that limits that electrical conductivity of our thermoelectric materials. We don't want this. We want the electron to separate from the ionized dopant. And that is again where the chemists come in, because they can manipulate this by adding very clever bits of molecular structure to the semiconductors. They can reduce this type of interaction strength. And that has proven a very successful strategy that has allowed us to make really much better materials. We have simple glass substrates, just a piece of glass. I mean, of course, it's very flat, and we clean it extremely well. Then we deposit our material plus the dopant, and then we have a nice little thin film of our semiconductor, and then we can, just by basically like a current meter with a voltage source, we can measure the conductivity. I always thought that I understood how charges move, so conductivity, electrical conductivity, I thought I understood that relatively well. And then you move to doped systems, so a different regime of conductivity, much higher conductivity, and all of a sudden everything is very, very different. If you're into curiosity-driven research like we are at university, then that is where things get exciting. It's like, oh, all of a sudden I have no idea how this works, right? That is basically where you want to be.